So after we've drawn in the plane of the determinant and trace values of your Jacobian matrix the line d equals 1 4 t squared, where the trace was a plus d, and the determinant was a times d minus bc, where the Jacobian was a, b, c, d. So this is where we are. Then the eigenvalues were the solution to a quadratic equation with two solutions. Now we can analyze those eigenvalue solutions, and it turns out that we can draw this line. And if you think about the lower part, okay, so let's mark that in blue. So let's say d is smaller than 1 4 t squared. Yeah. So d is smaller than 1 4 t squared. Right, that means that t squared minus 4d is greater than 0. Then lambda is just a real valued number. Okay, say 0.1 or minus 0.3. Okay? Okay, so that's the case that you get then. And otherwise, when the d is larger than 1 4 t squared, now we're in this region, t squared, then t minus 4d, right, is negative, and we have to take the square root of a negative number. Yeah. Well, that's something rather unusual. That can be done when you have a certain definition of what is called the imaginary part denoted by I. You can forget about all of this because in the end we don't need that. The only thing that you need to know is that in this region you have oscillatory solutions. Right? And so when this occurs, you have oscillatory solutions. And in the blue part, so this is oscillatory. And in the blue part, you have exponential dynamics. Okay? So that means close to the steady state, if this holds, then either, if this is the steady state, the system, the perturbation goes like this, or the perturbation goes like that. So here it's stable, there it's unstable. Yeah. And here it's oscillatory. So either you have, so if this is your steady state and you give the perturbation, either the system oscillates but has a damped oscillation to the steady state and you have stable case. But what you can also have is that around, if you start around the steady state, that the system actually has stable oscillations and then it's unstable, right? Okay, so these are the two options here. So if d is smaller than 1 4 t squared, you get exponential perturbation decays. Okay. Okay, and the other thing that, so we both have, in the blue part you have stable solutions and you have unstable solutions, and in the red part you also have stable possibilities and unstable possibilities, right? And the stability is ultimately determined by the eigenvalue, but what is called this real part. So in the general case, right? So you get something like this, like value number plus q times this imaginary number. This imaginary number either occurs or not, and that depending on whether you're there or there. So this is the real part of the eigenvalue, and this is what is called the imaginary part of the eigenvalue. Now if the real part of the eigenvalue is negative, right, then you always have stability. Right, so that's the rule. Okay. So the real part of the eigenvalue assesses the stability. Okay, and the real part of the eigenvalue is always the trace. Yeah. Okay, because that's also, so if this is negative, right, then you get the square root. So if you have the square root, say, of minus 32, right, then you have the square root of 32 times minus 1, and that's always going to be something like a value, so the square root of 32 times the imaginary number, right? Okay, so the imaginary number always comes from here. Yeah? So the real part, so the sign of the real part is determined by the trace. So that means that if the trace, okay, so that is just the trace, well, in fact divided by 2 if you look carefully, then, but so it's the sign of the trace that determines the sign of the real part of the eigenvalue, and this determines whether you're stable or unstable, because if the trace is positive, then you're unstable, and that's when the real part of the eigenvalue is positive, and that means in this case that the fluctuations do not damp, right? So you get these stable oscillations. Here the oscillations damp because of the negative real part of the eigenvalue. And if you don't have these imaginary parts, then either you have a negative eigenvalue or a positive one. So a positive trace or a negative trace, right? Now, all this part about these imaginary numbers, in principle you can forget, because what you can do, you can assess the stability and the nature of the steady state from this plot. Then we add one more piece of information to it, is that all the steady states at negative trace values are stable, and all the steady states at positive trace values are unstable. So that means that here, in this region, we get stable oscillations. Here in this region, you get damped oscillations. In this region, if this is your steady state, you get exponential decay back. And in this region, if this is your steady state, you get exponential rise. Okay? Now, in addition, things of course happen when you're at these lines. Right? If you're at the T line or the D line or on this curve, particular behaviors happen, and all these behaviors are documented in the syllabus. Okay? So that means that if you want to assess the stability of a two-variable system, then the only thing that you need to calculate is the Jacobian matrix. Step 1, the determinant and the trace values. Step 2, then you mark the T and D values in the curve, in this particular plot, and then you know, in this particular case, you have a stable, what is called a spiral So the dynamics spirals around the steady state. So you have the general oscillation, okay? So that's how you do it. So you don't need to know anything about imaginary numbers in the end. If you do, I mean, it's useful. But to assess the stability of a two-variable case, you actually don't need to know that, okay? So that's it for this part. So now we understand how to analyze the stability of two-variable systems by evaluating the Jacobian determinant, trace, and the determinant. And then for each steady state, you have a new value, a new matrix, a new Jacobian matrix, so new trace and determinant values. So if I would have a phase portrait, y and x, with null lines that intersect 3 times, then this steady state may lie here. That steady state, we want that one to be unstable, so that could lie here. And this one, the third one, could lie there. Okay? So given the phase portraits, you know how where the different borders are. Right, so the different regions are, so you can indicate, so here how many regions do we have? So let's say it goes like this, right? Then we have sine regions of dx dt here and there, so these are different the regions where the signs of dx dt and dy dt don't change. If you cross any of these null lines, of course you may jump to different regions, or to these, right? And when you cross the null lines, we know that the signs of the dx dt and dy dt changes. At the intersections, we know the steady state. The stability of these steady states can be assessed by this trick. So this completes the analysis of a phase plane and a phase portrait. Alright, that's it. Thanks a lot.